From EE Tech and All About Circuits, this is Moore's Lobby. I'm your host, Daniel Bogdanoff. Today's guest spent his early days using smuggled electronic parts to build radios as a teenager in India, and now he's a senior director building the world's most coveted AI compute system at the world's most valuable company. I'm joined by K S Venkatraman, Nvidia's senior director of AI computing, where he focuses on AI adoption for economic, education, and workforce development. He has long been involved with local government and academia, where he aims to make a difference in the technology pipeline. He's also spent time at Hewlett-Packard and Intel and has multiple patents related to processor design and operation. Venkat, thanks for being here today.
Thank you. Happy to be here, and thank you for having me.
I'm curious, how did you first get into the world of tech, and is it something you always knew you wanted to do?
I believe so. I grew up in a very academic family. My dad was a professor of chemistry, my mom was a professor of physics, and I've had this curiosity to understand how things work. So I would take them apart, break them, try to put them back together, almost always successfully. And sometimes I figured out that the best way to learn is by building things and seeing how they fail. So I had an early start in the field of electronics. And built radios and antennas as growing up as a teenager. It was very hard to acquire components because I grew up in India. And the only way you could get access to some solid state components was to go to the customs smuggled goods areas where they would resell smuggled products. And so I remember picking up a 9 megahertz crystal filter and building a radio transmitter with it. And the component that was the hardest to find was an RF power MOSFET for the final stages of RF amplification. I found something, cobbled together something with a couple of transistors and put up a dipole antenna in my backyard. And I was able to make a few contacts, particularly stateside, to some people in California. And that got me completely hooked onto electronics. And I knew that's something I always wanted to study because I just was so fascinated. It still is pure magic to me, even after the internet. So I pursued a degree in electronics and communication engineering, and then decided I wanted to specialize in electrical engineering. So I came to the US for a master's degree in electrical engineering, but then started getting interested in how computers work and switched to computer architecture and majored in computer engineering. And so that's how it's just growing up, I was fascinated by technology, particularly electronics, and started getting involved in computers. It was the initial days of the internet, very fledgling days of the internet. And if you just put your course description in a static HTML page, companies would call you. And so I had calls from Sun and Intel and Digital at that time. They were up in Boston. So interviewed with them. I liked Oregon the best because of its greenery and decided that I'd come here and work for Intel. So I never left.
I love the idea of this, kind of teenage kid having to go find smuggled black market parts to assemble a radio.
Yeah, I was away from radio for a really long time because, work and life get in the way. But during COVID, when we were all devoid of social activity, I decided to get back into it and built a small radio shack in my backyard. I knew nothing about construction when I started, but just watched a whole lot of YouTube videos and put together a foundation and built a 200 square foot structure from the ground up and dug a trench from the house to the backyard and got coax and Ethernet and power and even a water line and built up this shack. And now I have an HF radio with a wire antenna strung up an oak tree. And I'm able to talk to people all over the world with that. So it's been a lot of fun getting back into the hobby.
So what's your call sign if people are listening?
Oh, it's K7 VKT, Kilo 7 Victor Kilo Tango. And the VKT suffix is just a short form of my name.
I love that. That's awesome. Going back to your roots a little bit, you spent some time at different careers. You put your CV and your phone number up on the internet. And I think I heard you say you got a job that way.
That's right. Intel found me through a static HTML page that just listed my course description during my master's program. And they called and said, we see that you've been doing computer architecture and we're a site designer and we'd like to talk to you for our processor group. And so I had a phone interview with them. They decided to fly me out to Portland, to the Hillsborough area. And we had a whole day of interviews talking about computer architecture. And I didn't realize which project they were hiring me for. It turned out to be the Pentium 4 architecture team, design team, actually. It started with design and validation. And then I moved into architecture. This was the early days of x86 moving to 64 bits. So when that happened, I was involved with redoing the architecture for the page tables because memory management changed with 64 bits. So I worked on Prescott, which is the first 64-bit Pentium 4 architecture, and I was involved with a lot of post-silicon competitive analysis because if you recall, AMD had come out with their x86 64-bit architecture, and they were a little bit more power efficient than Intel was at that time. So there was a lot of push to try and extract as much power efficiency as possible. Intel just chose a deeper pipeline to push frequency, and AMD took the other approach. So I did some post silicon bring up, some competitive analysis work, and then I moved full time to the architecture team at Intel, developing the architecture for the Nehalem processor. And that turned out to be the core i3, i5, i7 series that you still see today. And I was architecting a technology called hyperthreading for Intel. So this is the idea of having a physical core, but having virtual processors inside of it. So we called it simultaneous multi-threading, which the marketing name was hyperthreading. And when the architecture definition for Intel completed, I got bored again. I switched groups at Intel 8 times just because I wanted to do something different. I would find myself getting pigeonholed very fast. So after I'd exhausted different groups in the processor division, I decided to leave Intel to do a startup company, and that is how my I was able to unfurl my wings, so to speak, and learn a whole lot more at the startup I went to.
So you spent a little bit of time at the startup. Can you talk about briefly what you did at the startup and then how you eventually transitioned over to Nvidia?
Yeah, so the startup company, six of us left Intel to do the startup company, and we were building SoCs for high definition televisions. So systems on a chip for high definition televisions. And, in hindsight, what went wrong was that we were completely funded by AMD. We had corporate funding, we had no VC funding. And so we were building an x86 processor, extending the instruction set, doing some media processing to it. And it was an in-order CPU that we built from scratch. We couldn't find something that AMD had that fit the power and performance envelope we were looking for. And the project was immensely successful up until the point where, before tape out. And two things happened. One was that the strongest champion for our startup company was the CTO of AMD, and he left AMD. And so we lost that really strong connection, coupled with the fact that AMD acquired ATI Technologies. And they had a digital TV team. And so they said, we don't really need you guys anymore. And we'd grown from 6 engineers to about 80 because we were doing not only the integration around the SoC with third-party IPs, we also had an RTOS team and a large software team. So we'd grown to about 80 engineers, and then when everything folded and we didn't get our last round of funding, our CEO at the time, Randy Steck, he was looking for how to place people, and so he knew Jensen, and he said there's some good people up in Oregon. So Jensen came. He came with 20 of his staff, and they interviewed all 80 of us within a day and picked up 20. And that's when we started an NVIDIA office here in Hillsborough. So I joined NVIDIA in 2006.
Well, Nvidia in the last, few years especially has had quite the meteoric rise, I would say. Always a well-established and well-respected tech company, but as this wave of AI has started to swell and really build up, Nvidia has been, kind of the darling of the space. Can you talk about when you realized AI was going to become a thing, and how long did it take the rest of us to get on board?
Yeah. So a little bit about NVIDIA, I think, is a good backdrop to this, just because the culture at NVIDIA I found was very different from what I'd experienced at Intel, and including the startup company. I knew nothing about GPUs when I started, right? I was a CPU engineer all my career when I joined NVIDIA. And so, typical NVIDIA style, we get thrown into the deep end of the pool to see if we can sink or swim. And I had to quickly learn. I knew nothing about how graphics pipelines worked. The first product I worked on was called Fermi, which is the first DX11 GPU. And so I had to learn a lot about geometry and tessellation and how graphics works. And it was a completely different concept, throughput computing versus latency computing. And
Yeah.
so that took a little bit of getting used to. But then NVIDIA decided that it wants its own CPU strategy. And because many of us had CPU experience, Jensen asked this team to go build the first ARM 64-bit CPU. And so that was my first project at NVIDIA. After the first GPU that I worked on, pivoted back to CPUs and built the um, the Denver processor, and that went into the first 64-bit Android tablet. So we partnered with Google. They released their 64-bit Android operating system called Lollipop, and we had our first 64-bit ARM SoC. So, and it was really good to spend 2 years on that project and then finally have something that you can touch and feel, that's really your hard work. And it was a very novel architecture because it was a hardware software co-design project and used a dynamic compiler to optimize code, and very responsive. So that worked reasonably well. But then to your question about when did I know that AI is going to become a thing, I did not. Frankly, every 2 3 years I have this itch to go do something else, and so after the CPU project ended, I felt like that took a lot out of me because I was spending close to 15, 16 hours a day for 6 months straight, bringing up the silicon and getting the software up. And so I again wanted to do something different. And I talked to a few leaders at NVIDIA, and they said that the GPU computing team is looking for some management bandwidth. So why don't you go talk to a few leaders there? So I did. I spoke to my boss, who's still my boss today, and he asked me to go work on system architecture for a GPU called Volta, and trying to connect GPUs together using NVLink, which is a high performance interconnect that we still have. So while I was working on Volta, um, high performance computing was the use case for multiple GPUs, scientific computing and parallel computing, solving all kinds of numeric solvers and weather forecasting and those kinds of applications. But I've always believed that once you have more computing available, then applications show up. And this is the case in point with AlexNet. I think that is really the pivotal point where computer vision became very, very good, to the point where it was far exceeding some of the OpenCV kind of algorithms, so traditional computer vision algorithms. And now, if you look at it, computers have just become superhuman in the space of vision and language. And even one of the big application areas was recommenders. And so that progression for the technology, I think, was the pivotal point to your question, was really computer vision neural networks or convolutional neural networks that help computer vision algorithms.
When you're designing for like a processor that you know is going to be used for CNNs, what's different about like an AI processor versus a latency-based or a throughput-based processor?
So the fundamental difference, I think, is that I think the way to appreciate this is how did GPUs become useful for AI? And the way I think about it is GPUs are inherently parallel in nature, right? Because if you think about every pixel on your screen that needs to be lit and colored, that is independent of every other pixel on that screen. And displays are getting bigger. And so you need a lot of parallel computers to do that, to render images. And so you already have this massive parallel computing capability available. And if you allow it to support multiple math formats, then that just makes it an ideal computer or ideal supercomputer to solve very complex problems. And so that is how I think researchers use GPUs and used it to adapt it to different kinds of problems, and um, that is how that growth happened. And I say two things that have really helped the AI revolution is one, the availability of large amounts of data, right? Because we're all walking around with our phones and generating data. That's just one example. But data has grown, and then the computing capability has grown. And you put these two together, and magic happens. And that is how I think the AI revolution got started. We have this growth in accelerated computing, which is far better than Moore's law. And so if you look at the scaling of how CPUs did really, really well following Moore's law. But over time, that progression has stalled. But if you look at how accelerated computing has taken off, that is just phenomenal. And so we are seeing growth that is just unimaginable, almost exponential, which is hard for us human brains to even comprehend.
Yeah, I've been thinking a lot about comprehend. This is going to sound really nerdy, but I've been thinking a lot about how like my mental models work for linear versus exponential versus cubed, and it just it's like I'm so bad at anything that's not linear.
Yeah.
Like all my guesses are complete garbage.
That's right. So if you think about the scale, we've had 1,000x increase in AI computing capability in just 8 years. And so long ago, sometime in 2001, there was a Wall Street Journal article with Jensen's quote called Huang's Law, where he said that silicon chips that power AI will more than double in performance every 2 years. And this is attributed not just to the hardware, but to hardware and software. And so it's really the hardware software co-design that comes into place. And if you look at the kind of computational capability that we have with Hopper and then the leap to Blackwell that we announced recently, it's just phenomenal. And you're right, it is on an exponential curve, which we like to call the hockey stick.
Yeah, yeah. The business and marketing folks love the idea of the hockey stick,
That's
don't
right.
we?
That's right. And one point, sorry, just to tell you that even though the computing capability has increased so much, with the invention of transformers, which is another pivotal point, and so there is a paper by Google Brain researchers called "Attention Is All You Need," and that was the other big transformational change that happened because that was the invention of transformers. And so large language models have benefited a lot from the scale in computing capability. And so if you look at the parameter sizes for some of these models, they have been doubling every 6 months. In fact, the latest model from OpenAI, there's a GPT mixture of experts model. It's like 1.8 trillion parameters. So this requires, order of exaflops of computation power. And so the applications have kept up with the rise of accelerated computing.
It's funny how we manage to find uses for the technology that we build. It's like I see that with 6G as well as like there's not really a clear idea of why we need that full data rate. Like there's not one killer use case that just drives the technology forward. But what we've seen with other like wireless technologies is as soon as we can send video, then boom, we're watching video on our cell phones,
Yeah.
which was something that wasn't really in the initial parameters. Where do you think we're going from a processing level? And if you had to put on your, AI weather forecasting hat, where do you think this is going in the next 5 or 10 or even like 30 to 50 years?
So I'm very bullish on technology just because I feel like it can be used to solve some of our toughest problems. If I think about education or adapting to climate change, or with the energy transition or healthcare, these are some problems that I feel AI should be able to help us solve. And you asked about a long term horizon. So, in addition to solving complex problems, I think humanoid robots are going to become fairly commonplace over the next decade or two. and they can be used for physical, mental, and emotional support, which is pretty big if you think about it. I know there are some startups now that have already started doing some work in this area. Boston Dynamics is the one that comes to mind, but there's one in San Francisco, and so is Tesla. And then when I talk about education, I feel like there is a very personalized component to education that AI is going to help us with. Every student learns differently. And so that removes the burden from teachers to be able to use these tools to benefit everybody. And those are the things that keep me motivated about this technology. And I think there is a lot of good that it can be used for. There is a certain amount of complexity that people need to understand, and there's a certain amount of fear about the technology itself. But I feel like students embracing it to use it as a tool to solve complex problems is the best thing they can do. Very recently, we I was sitting on an interview, and there was a student, and the question that I asked him was, "What problems have you solved using AI?" And so his answer was interesting. He said, I have a backyard with produce, berries and vegetables, and I had squirrels eat up most of the produce. And so I used security cameras and a Raspberry Pi, downloaded a model from the internet, and I trained it with thousands of images of squirrels. And now when I detect a squirrel, it turns on the sprinkler system. And so he solved a real world problem, using this tool. And he got his hands dirty, rolled up his sleeves, and figured out how to train a model and and use it and put it to some good use. So that is a skill that is really, really helpful.
A 21st century scarecrow. That's amazing.
Absolutely. Yeah. Yeah. And so this is why I keep, because I also serve on the education board, like the Workforce and Talent Development Board. I'm trying to influence the entire talent pipeline from K through 12 to community colleges to our public colleges and universities, and trying to infuse AI curriculum throughout. And I think that's incredibly important because this technology is here to stay. It's so revolutionary. In my generation, I feel incredibly lucky to have gone through the internet, the revolution, and then the mobile revolution, right? I mean, PCs were there a long time, but nobody could have predicted the number of jobs that these technological revolutions would create. When we had ATM machines, people would say, hey, all these bank tellers are going to lose their jobs. But that wasn't the case because despite ATMs, tellers started offering more services. And similarly, with the Industrial Revolution, we had tools that would take out the drudgery of the repetitive work that we had to do in the fields, and so that's increased productivity a big deal. I feel similarly about the next AI revolution, and that's really the generative AI revolution, which is just mind-boggling.
It is. And I think when I put my electrical engineering hat on and think about the folks listening and watching, when it comes to like electrical engineering tools, we've interviewed some folks on the podcast that are doing startups for circuit design and schematic design and layout, very specialized. They require a lot of knowledge and domain experience to do this well, and here comes some AI companies that are starting to solve these problems and not necessarily replace traditional engineers, but solve some of the same problems that they're used to solving themselves. When it comes to the world of electrical engineering, where do you think AI is useful, and how should engineers start to think about how AI can help them solve their hyper technical problems?
Yeah, so that's a good question. The reason, so I think it doesn't matter which field you're in, right? You should always think about how can I use a tool to improve my productivity. And so, um, if I take electrical engineering as an example, there is a lot of design tools, place and route algorithms, EDA tools that are starting to use AI. So, um, removing anything that is repetitive in nature, and it's going to make us a lot more productive. The basic coding is solved through a language model, but remembering how to think algorithmically to solve complex problems is a skill that people need to develop. And there are agentic AIs now that can, take a problem, break it down, and solve it for you with independent models. But at the same time, the human in the loop is incredibly important. And so I would just tell people who are in the industry to think about their day-to-day lives because it's very diverse. The kind of work that you do could range anywhere from a high-level design specification to architecting a piece of hardware or a logic or a piece of logic somewhere, and then writing RTL to go describe the hardware, and then doing some timing analysis on it, and then some place and route, and finally the physical design component of it. And each step of the way, you can figure out how to make that a lot more productive or how to make the tools more productive using AI. There will be off the shelf tools that are available from EDA companies, but I think at the same time, having a co pilot by your side to help you is going to be incredibly important. One thing I'd just like to say in conclusion to your question is I don't think jobs will be replaced by AI. Jobs will be replaced by people who know how to use the technology.
Mm.
So that is incredibly important. Just embrace it and use it and don't be scared of it, I guess.
Fair enough. Well, speaking of embracing it, this episode of Moore's Lobby is brought to you by Mouser Electronics. As your design fulfillment distributor, Mouser is your authorized source for millions of components from thousands of leading brands. Come discover, design, develop. And now back to Venkat, Senior Director of AI Computing at Nvidia. Can you walk me through like a AI tech stack? So let's say I have a problem I need to solve. Maybe there's a specific, maybe there's a chip design problem I'm trying to figure out, or it's, repetitive and I don't want to have to do it every day. How would I kind of start to finish think about the building blocks I need to solve that problem?
The best way to do it is to describe your problem in human language. And so the prompt engineering aspect of this is crucial. The output of these language models are as good as what they're fed with in terms of not only what they've been trained on, the data they've been trained on, but the prompt that you use to solve it. If you have, let's say, you have some kind of a logic problem that you're working on, but you write it from scratch using Verilog and you find that there are bugs in it, and you can test it using AI. So, for example, you can say, here's my piece of code and paste a snippet in there and say, I'm worried about corner cases and what kind of test vectors should I generate? So the tool can help you do that. But you have to tell it, you have to explain to it what you're trying to do, what the outcome you expect is, and what help you need. And so it'll just be your co-pilot and generate what you want for it. And similarly, if there are timing problems that you want to understand and any kind of slack you have on your timing paths, it'll help you understand how to optimally place your devices, etc. So it's unlimited. I mean, what you can do with it is just think of it as something that knows everything. And so you can just ask it any question and it'll be able to help you.
Okay.
One of the things that I want to mention is, we spend a lot of time in companies training junior engineers, right? We hire them out of school, but they don't know what it's like to work. And so there's a lot of time experienced engineers spend where to find something or where to go for a resource or how to solve some of the simple tasks that junior engineers come across. And that is where a language model can really help you. Think of a chatbot, that is an experienced chatbot, something like a principal engineer. And so it can teach the junior engineers how to go about their day-to-day tasks. So that's an incredibly good use of that technology. Ramping up.
Clearly, in your personal life, you're someone who likes to learn things and then apply them. For example, your Radio Shack in your backyard. And education is clearly something that's important to you. So maybe we circle back to that for a moment. How should AI be used in schools? Because you see like media will reference things like a student connecting a language model to a 3D printer plotter and writing an essay for them. Obviously, that's not the type of learning experience we want them to have with AI. What does that kind of co-pilot education experience look like, K through 12, but also in the engineering world?
Yeah. So one big thing is introducing the fundamentals of AI, how to train a neural network, how to run inference on it and deploy it to solve problems. That is something I think is important for students to learn. Um, and it's different at every stage of the talent pipeline. K through 12, I think it's more using the technology to understand concepts and for teachers to use it to provide that personalized education experience that I was talking about. I don't think AI needs to be a course in itself. Earlier I was thinking about having a fundamentals of AI course in K through 12 and making that a graduating requirement. I've since moved away from it just because the system is so complicated that graduating requirements are very hard to influence. Uh, there's a pushback from the Department of Education, from teachers' unions, and it's just very hard to make something a graduating requirement. Rather, it makes sense to infuse it in existing curriculum because it's so pervasive. The technology applies to every economic sector. It doesn't matter if a student is interested in the science or the arts or even music. So there is AI everywhere. But learning how to use it as a tool to solve problems is the most critical aspect at K through 12. At community colleges, I feel like there should be a more specialized AI program where students can show, that they've used the technology to train a network, deploy it somewhere to solve a specific problem. And the field is changing so fast that it's very hard to keep up. And so when you start thinking about curriculum at universities and colleges, we've always had this problem where technology advances more rapidly than curriculum can keep up. And now that's even more the case. In fact, this field, by the time you come up with an idea and you say that you want to present it at a conference, by the time that conference comes up and your paper is reviewed, it's already outdated. So keeping up with it is super important. And so there are lots of accounts, for example, there are people who do research on AI and they share what they find on social media. Like there's some accounts on Twitter that are that you can follow and you can get the latest information about what's new and what's happening. So keeping up with the technology is critical for people who want to get into the field. Now, I say want to get into the field of AI because it need not be the case that you have to develop AI systems. It's more important to be able to use them. You don't need to be a mechanic to drive a car, right? So, but if you're interested in it, sure, then you have to keep up with the technology. That becomes a challenge with how fast it's evolving. But using the technology is critical. And so K through 12, I think it's more using the technology at our colleges and universities. It's about having AI programs that teach you the fundamentals of neural networks and how to train them, use them to solve problems. You talked to me about that kid with the large language model and the 3D printer. And so coming back to education for a moment, I think it's important that our educators know what's important and how to teach it. So, and that example came to a high school teacher who insisted on handwritten homework. And so this kid hooked up a 3D printer to a large language models API to generate handwritten homework. But I'm sure that kid learned so much more from that project than anything we teach at high school. So that's why the hands-on learning is super important.
Yeah, and going back to your concept of you don't have to be a mechanic to drive a car. It's still helpful to like know how to change a flat tire or
Absolutely.
maybe even change your oil. When it comes to the ethical use of AI and AI security, what's the current mindset for how to tackle this problem? And are there any official groups that are working on it?
I think that some of the things that's in a lot of people's minds is about the technology and its safety and risks, etc. So I can just briefly mention that I was a part of a working group at NIST, which is the National Institute of Standards and Technology, and they're taking this fairly seriously, mainly to advance the science of AI safety. And they're developing standards and guidelines. And there's global engagement. There are over 200 companies that are part of this effort. So there is already a risk management framework that they're looking at. And so they want to understand real world impact with a lot of collaboration and coordination among companies and agencies. So I'm happy that that's happening because it's important. And the key part is to leverage the good parts about the technology while while being aware of the risks involved. So that comes up a lot.
When it comes to if you were to develop an AI curriculum, uh, what sorts of skill sets would you think people need to have? Because for engineers today, we don't necessarily have the luxury of going back to school, but we're all experienced learners, and that's kind of how we've gotten into this field is taking on a challenge and learning it. What sort of curriculum would you put together for a engineer that's looking to learn more about this space?
Yeah. Something that may be surprising to you at the top of my list is actually not anything technical. It is human skills. And the reason I mention that is because skills like collaboration, communication, empathy, um, self critique, the ability to understand and realize that you've made a mistake and more importantly, learn from it, and critical thinking. These are some skills that I would put at the top of my list. The second would be getting used to lifelong learning. Your education isn't over with a college degree because this piece of technology is advancing super fast for anybody to keep up. And so you have to continuously adapt and figure out how to use the advances to help you in your career, whatever it may be. It could be a legal profession. It could be something to do with an administrative position. It could be anything, but understanding how to use the technology and keep up with it and learning the advances and putting it to good use. And third, the problem solving that I mentioned. We are, so basic problems, computers are getting to the point where they can solve them for you. But the very complex problems require a lot of collaborative human interaction, which is why I put those human skills at the top. And in addition to these, the next are the things that I mentioned earlier, which is the hands-on projects. Just just teaching the basics of AI and robotics, and for students to learn by doing. I think that's incredibly important. And the cross-disciplinary part of curriculum is also critical because it's no longer something that applies only to computer science students, right? Just the field applies to every economic sector. We like to keep saying that education lifts all boats, and I think most of us agree with that. But this technology can lift all economic sectors.
Can you give me an example of a complex problem that requires a lot of human engagement?
Yeah, I think no single person can go build a processor, right? So
Sure.
the first thing I would think of is if I reflect back on my career and how AI could have helped us is all these collaborative meetings we would have in a room trying to understand microarchitectural corner cases, right? So, we would go through manually written test plans, and it's only a few of us who would review that in isolation and trying to identify corner cases. But obviously, the bugs would all be there, and you're only as good as what corner cases you can think of. But if you had the technology to be able to go generate different kinds of text vector, not just random tests, because those can solve a certain amount of problems, but still you have lots of escapes. And I think in the validation environment, AI can be immensely helpful, generating test plans and test vectors to do a high quality product in a short amount of time. And that is something that requires a lot of collaboration to train the model to be able to do what you want. That's one example that comes to mind. But we have so many complex problems today that require the use of technology to solve. One big thing is weather prediction, and so you have Traditionally, how we have done this is we've used first principles physics equations and to feed in a whole bunch of vectors of current weather conditions, and these would be things like the current wind or the humidity or the pressure, and then we feed that into these partial differential equations, and that comes out with a probability ensemble. And that's the reason. But these probabilities that we generate is also dependent on the current weather conditions, and therefore the probability distribution that comes out of it, it's only valid for the next 2 weeks of it. That's why our phones, when we look at the weather on phones, we don't get accurate predictions any more than 2 weeks. And this is another area where I think AI is super helpful for two reasons. One is that it can mitigate the enormous amount of money we spend on it. Like, for example, just climate related fatalities and climate events have cost us about $150 billion over the past year. And some examples of these are the R Valley and Hurricane Ian, if you remember. And in Pakistan, we had floods. Now, with the help of AI models, we are able to narrow down the large scale weather predictions down to kilometer scale. So that is incredibly helpful to find micro climate events, and it can save lives and be very accurate. And so these are things that help us, help humanity overall. And I think this is where technology should be put to very good use.
Hmm.
There's many other examples in the healthcare field and energy, and energy transition is incredibly important, but I think AI can be helpful. So,
What is the individual consumer's responsibility and the corporation's responsibility, from your perspective, to make sure that we are ethically sourcing our training data and ethically inferencing these models
yeah,
in a way that's safe and
Yeah,
ethical?
so the ethical use and fairness comes down to being transparent about the data that's being used to train the models, and then what are the models actually being used for. And so there's smaller and more efficient models, some open source models that are coming into play. And from a government, corporations can be transparent about the models they're using and what data was used to train them, and from a government's perspective, as they come up with regulations, just developing some standards and guidelines that make sense from a risk management and governance point of view. But governments can't do it alone. There needs to be a lot of collaboration and coordination with different companies, which is why I think NIST is the right place, like you pointed out, to do it, because there's a consortium of over 200 companies providing inputs, and they seem to have come up with a good first step in terms of working groups and task forces to address the need. So governments have their
Wonderful.
own role to play, but at the end of the day, I think there's a public-private partnership that needs to be involved to make some common sense rules and regulations. And there are already existing rules that can be enforced and leveraged to regulate AI, and then add others where it makes sense. In the US, regulations have been a mix of federal and state and local efforts. But in the EU, they've been a little bit more proactive with the AI Act. And so I think these will happen. It's important for there to be regulations. But at the same time, there needs to be an understanding of the benefits and the trade offs. As individuals, I think the best we can do is to keep an open mind, have an independent, critical thinking mind, and see if the information makes sense and evaluate it for what it's worth. But take the good parts of it.
And when you think about like the automotive industry, there's already that corporate and government partnership to make, roads safer, vehicles safer, and there's collaboration on developing like,
Proceed.
seatbelt standards and that
Yep.
sort of thing.
Yep, absolutely. You're right. One other issue with which comes up often that we haven't talked about is the energy use, right? Because data centers are consuming more and more power, and accelerated computing helps because it's the most important, most efficient form of computing there is. But at the same time, I think AI can be used for optimizing um, the energy grid or the power grid, like the power plant operations, fuel costs, and then sourcing the power at the right time, the mode of power, whether it's a renewable power source or something like that, and making the grid a lot more resilient. And I also feel like the energy demand is going to continue to grow in the future, and investing in alternate sources of energy that are carbon neutral, for example, small modular reactors, nuclear reactors, are incredibly important, particularly thorium fueled ones, because thorium is a very abundant fuel. And if you're able to leverage the technology that we had developed in the 60s from Oak Ridge National Labs, they had these molten salt thorium based reactors. And that research never really made it into reality. But other countries are progressing with it. For example, China and Russia. They have assembly line manufacturing of these small modular reactors that can fit in a shipping container and they can transport it to where energy is needed. And, and that kind of technology is what the US needs. And so there's a lot of policy changes that need to be implemented to be able to make this technology a reality. But we absolutely need more energy.
I look forward to the nuclear fusion keynote or podcast. That will be a fun one for me.
Okay, cool. And
We are just about out of time. We like to do a lightning round at the end of these, so a couple quick questions, quick answers. If you had a magic wand and you could solve any AI problem or roadblock, what would you use that magic wand on?
I think the biggest problem is the talent development pipeline. If we could infuse AI curriculum everywhere in the talent pipeline, then I think uh, the quality of students would be far better, and I think it'll serve our students better, student community better, if we could seriously think about how to do the infusion.
What is the strangest use of AI that you've seen? Maybe the most surprising that's come across your desk?
The strangest was when Stable Diffusion came out. I thought, going text to video, it was just mind-boggling. And the kinds
Yeah.
of videos you could generate, and it's very hard to distinguish what's real from what's AI generated till, all the lawsuits started happening, and then the watermarking technique came aboard. But to me, that text to video was just mind-blowing.
Yeah.
Because we had the shift from discriminative AI, right, to generative AI. And so discriminative AI just said that I have things, I can recognize them, and I can tell you what they are. But then to go the other direction with these multimodal models has been a big shift. Yeah, I didn't see that coming so fast. And
I think of Will Smith eating spaghetti, as as a nice benchmark for that. Well, thank you so much for your time. This has been really interesting and exciting for me.
thank you, Daniel. All the best.
That was K S Venkatraman, Nvidia's Senior Director of AI Computing. Thanks for joining me today in the lobby. It's a privilege for me to get to talk with industry leaders like this and share it with you, and it's only possible because you're out there listening right now. If you liked this episode, please hop on social and share it with someone that you think will like it too. That's how we get to grow and make Moore's Lobby better and better. And also, thank you to Mouser Electronics for sponsoring this episode. I'm your 100% real, definitely not AI host and friendly neighborhood geek, Daniel Bogdanoff. Thanks for listening, and I'll catch you next time.